So far in this course, we have considered electric charges that are stationary. Now we will consider the case of moving charges, that is, electric current. Consider an electrically neutral conductor. Imagine that we can see the positive and negatively charged particles inside the conductor. Suppose the positive charges inside a conductor begin to move. An electric current is now flowing through the conductor from left to right. The quantitative definition of current is the amount of charge that passes a point in a given time interval. The current I is equal to delta Q, the net charge passing a point, divided by the elapsed time, delta T. Though electric current is a scalar quantity, arrows are often drawn to indicate the direction of the current flow. Now the negative charges are moving. In this case, the current is taken to be in the direction opposite that of the charges. The current arrows indicate the direction of motion that the charge carriers would have if they were positive. In metals, the charge carriers are negatively charged electrons, and their motion is opposite the direction of current flow. The net motion of all charge carriers must be added to obtain the total current. Here we show one conductor with moving negative charges, a second with moving positive charges, and a third with both moving negative and moving positive charges. Which of these three wires is carrying the greatest quantity of electric current? Correct. Now the whole conductor is moving. What is the direction of the electric current? Correct. Oppositely charged particles are moving in opposite directions, and both movements contribute to the total current. While we would not expect this sort of current to occur in a metal, it does occur in ionized media. Current is the net charge that moves past a point divided by the elapsed time. The unit of current is therefore coulombs per second, or amperes, abbreviated by capital A. If 2 times 10 to the 19th electrons passes a point on a wire in 5 seconds, what is the magnitude of the current that flows through the wire? Try again. Try again. Correct. Current is flowing through the thick wire connected to the thin wire as shown. Because the current can't pile up in a conductor, the current in the thick wire must be the same as the current in the thin wire. This brings up the concept of current density. If the current density J in a conductor is constant across the conductor, its magnitude is equal to the current I divided by the cross-sectional area A of the wire. Given this definition of current density, and the fact that the current I is the same in both the thin and the thick parts of the wire, which part of the wire has a higher current density? Correct. The same current is spread over a smaller area in the thin wire. A wire with a diameter of 0.1 centimeters carries a 5 ampere current. What is the current density in the wire? Try again. Correct. How fast do electrons actually move in a current through a metal? Consider a metal conductor of length L with a cross-sectional area A. The volume V of this section of wire is equal to A times L. The number of current-carrying electrons per unit volume is N. The magnitude of the total charge, Q, moving in the volume V is NeV, where E is the magnitude of the charge on a single electron. The current is the charge in this volume divided by the time it takes for the charge to move through the length of the wire. The drift speed V sub d is the magnitude of the average velocity of the electrons that comprise the current. The electrons also have random thermal motion that does not contribute to the current. The electrons move through the volume with the speed v sub d, which is equal to L divided by T. Now we have an equation relating current and drift speed. The result is that the current I is equal to the number of electrons per unit volume N times the charge on an electron E times the cross-sectional area of the wire A times the drift speed v sub d. By dividing both sides by A, we reach an equation that relates drift velocity and current density. This can be rearranged to solve for the drift speed. Let's plug in some typical numbers. For copper, N is about 11 times 10 to the 22nd electrons per centimeter cubed. We obtained a value of 640 amps per centimeter squared for the current density in a previous example. The drift velocity is only about 0.03 of a centimeter per second. Why doesn't it take hours for the lights to come on when you flip the switch? Even though the electrons drift along fairly slowly, they begin drifting throughout the wire almost immediately when the switch is turned on. Current density, unlike current itself, is actually a vector, even though so far we have considered only its magnitude. We can put the equation we previously derived into vector form to relate the drift velocity to the current density vector. The negative sign is present here because the charge-carrying electrons are negatively charged. When a voltage is applied across a conducting path, current flows through it. In this circuit, the battery applies a voltage V across the light bulb. The amount of current I depends on the properties of the circuit. Consider a conductor that has a voltage V applied across it and a current I flowing through it. The resistance is defined as the ratio of the voltage across a conductor to the current flowing through it. The unit of resistance is the ohm, and 1 ohm is equal to 1 volt per ampere. The higher the resistance, the higher the voltage necessary to drive a given amount of current through a conductor. The symbol omega is generally used to represent ohms. A conductor with significant resistance is called a resistor. We can rearrange the equation for resistance as shown. In this form, it is known as Ohm's law. Strictly speaking, Ohm's law applies only when the resistance R is constant over a range of currents and voltages. Here, voltage is plotted versus current for some resistor. The graph is a straight line. Since the slope of the line is constant, Ohm's law applies. The slope of this curve is not constant. Therefore, Ohm's law does not apply. Ohm's law applies for most resistors. Here's a problem for you. 5 volts is applied across a 2 ohm resistor. What current will flow through the resistor? Correct. Resistance depends on the geometry of a resistor as well as its composition. The resistivity, ρ, which is related to the resistance, depends only on the properties of the material. For a conductor of length L with a uniform cross-section A, the resistance R is the resistivity ρ times L divided by A. A nickel conductor has a cross-sectional area of 0.0025 centimeters squared and a length of 2 meters. What is the resistance of the conductor? The resistivity of nickel is 6.8 times 10 to the negative 8 ohm meters. Correct. Before moving on, we will introduce one more quantity, conductivity, represented by the Greek letter sigma. It is the inverse of the resistivity. If the resistivity of nickel is 6.8 times 10 to the negative 8 ohm meters, what is its conductivity? Solve this before moving on. Did you get the correct answer? When we studied electrostatics, we worked under the assumption that no electric field exists inside a conductor. When a voltage is maintained across a conductor, say for instance by a battery, an electric field can be maintained inside a conductor. We will assume the conductor being subjected to the applied voltage is uniform in composition and cross-section, and that its ends are equal potentials. Given these assumptions, the electric field in the conductor is uniform and directed from the higher voltage end toward the lower voltage end. Let the length of the conductor be L and its cross-sectional area A. The magnitude of the electric field inside the conductor is given by the voltage V divided by the length L. An electric field in the conductor will drive a current through it. Inside a metal, the electric field exerts a force on the electrons and accelerates them. Because they are slowed by interactions with the metal, as a whole they do not continue to accelerate, but instead, on average, the electrons move at a steady rate of V sub d. One might imagine the electrons undergoing periodic collisions and being slowed down. Further, the electrons have thermal motion, which we have not shown here, but which is much faster than their drift speed. To describe with accuracy the details of electron behavior, quantum mechanics is required. The electron's drift leads to a current with current density J. This is equal to the drift velocity times the number of electrons per unit volume n times the electron charge E, as we discussed previously. Because electrons are negatively charged, the current density vector is in the direction opposite that of the drift velocity. The drift velocity and the current density are proportional to the electric field. The definition of the resistivity is the electric field divided by the current density. For uniform current density, J is equal to the current I divided by the conductor's cross-sectional area A. Finally, substitute equations for E and V into the definition for current density. Note that velocity V divided by current I is the definition of resistance R. Now we have related resistance to both resistivity and the geometry of the conductor. This result can be rearranged to obtain R in terms of ρ, a result we stated previously. Electric current passing through a resistor heats the resistor. Electric power can be used for many applications, such as running a motor or generating heat, light, or sound. This toaster produces visible light along with heat. Let's quantify the energetics of an electric circuit. We will consider the simple case of heat production in a resistor. In the toaster, the resistor is a fairly long wire. The zigzag line symbol shown is used to designate a resistor in a circuit. Let the resistor have a voltage V across it and an electric current I through it. We will assume that this current is constant over time. The electric current from a wall outlet actually oscillates over time, but the arguments here still hold. The electric current, by definition, is the charge, delta Q, passing through the wire in a time interval, delta T. You have learned that when a charge delta Q passes through a potential drop V, its potential energy is decreased by delta U. This energy appears as heat in the resistor. The rate of energy transfer, that is, the power, P, is equal to delta U divided by delta T. Proceed to substitute as shown to obtain an expression for the power. The power P, dissipated in a resistor, is the current I multiplied by the voltage V. What are the units of electric power? Recall that the units of current are coulombs per second, and that volts can be expressed as joules per coulomb. This is equal to joules per second, or watts. Ohm's law relates current and voltage. We can use this equation to substitute for either V or I and obtain two more equations for power. If 400 watts of power is dissipated by a resistor of 33 ohms, what is the current through the resistor? Correct.